Welcome to today's Explainer. We're going to dive into a fascinating and, let's be real, incredibly frustrating problem in AI right now: why self-evolving agents often just crash and burn when deployed in the real world. More importantly, we're looking at a brand new framework called RSEA that completely fixes this issue. If you've ever built an agent that seemed to get smarter and smarter, only to suddenly collapse and forget how to do basic tasks, well, you're in exactly the right place.
Here's a quick look at our roadmap for today. We'll start with the agent context problem, then introduce the RSEA architecture, look at the held-out selection gate, dive into benchmarks and context collapse, discuss monotonic safety guarantees, and wrap up with some actionable best practices for developers.
All right, part 1, the agent context problem. Let's unpack exactly why unguarded agents fail.
So we really have to ask ourselves, why does adding more learned context to an agent's memory often act like a student cramming for a very specific test, but then completely failing in the real world? Right now, developers are increasingly trying to improve LLM agents without updating the underlying weights, because, fine-tuning is expensive. Instead, they evolve natural language artifacts, things like reflections, workflows, optimized prompts, and they feed these into a frozen model. But here's the massive catch. When agents curate this context online without any validation, they introduce insane amounts of variance. They're basically filling their context windows with high-variance heuristics. So on the surface, the agent looks like it's learning, but silently, it's losing all of its robustness. It's just accumulating unstructured junk.
This means we urgently need to make a shift. We've got to move away from risky, unguarded prompt accumulation and toward structured state management that prevents fragmentation. The old way, just blindly appending every new lesson to the prompt, leads directly to what researchers call context collapse. The model gets distracted, latency spikes, and generalization just tanks. The new way, which is our focus today, is audited context evolution. This treats the agent's memory not as some messy dumping ground, but as a carefully managed state.
Moving right along to Section 2, introducing the RSEA architecture, which provides a really elegant 3-layer solution.
The researchers behind this, Michael Nguyen, Quoc Nguyen, and Paul Vu, built RSEA, which stands for Recursive Self-Evolving Agent. Now, unlike previous methods, RSEA rewrites its own context, using a strict validation loop rather than just blindly appending information. Think of it like this. It treats context evolution as a constrained search problem. It proposes a change, tests it out, and only keeps it if it actually works on unseen data.
And you should definitely keep this rule of 3 in mind, because RCE maintains a very compact, easy-to-visualize state made up of 3 things: strategies, skills, and a playbook. Across different generations, RCEA completely rewrites all 3 of these layers based on its own execution trajectories. The imperative strategy guides the high-level approach. The reusable skills let it execute specific tool interactions, and the procedural playbook gives it step-by-step operational memory. By entirely rewriting these layers instead of just tacking things on, the state stays incredibly lean.
Okay, Section 3, the held-out selection gate. This is all about enforcing strict validation.
This 3-step recursive loop is the absolute engine behind that held-out selection gate. First, the agent generates a candidate state, a newly proposed rewrite of its strategy, skills, and playbook. Second, and this is absolutely crucial, it evaluates this candidate against a completely disjoint, held-out split of data. It's a proxy for unseen tasks. Finally, the Keep Better gate makes a ruthless decision. It ensures the candidate state is only committed if it definitively improves performance. If the new context makes things worse, the system just discards it and reverts to the base agent.
Let's dive into Section 4, benchmarks and context collapse. There is a serious plot twist in the data here.
To prove this actually works, the researchers tested RSEA across diverse environments like AlfWorld, Gaia, Talbench, and WebShop. They tested it against 6 baselines, including a standard React agent and a method called dynamic cheat sheet, all on a single shared local backbone for a totally fair comparison. And on the WebShop benchmark, the results are wild. An unguarded method like dynamic cheat sheet catastrophically drops to a 0.14 score compared to the vanilla React agent's 0.43. Because dynamic cheat sheet curates context without that strict held-out gate, it overfits to its training data, creates brittle context, and completely breaks under distribution shifts. It literally makes the underlying agent dumber.
But when we look at the ALF-World benchmark, the story gets even deeper. Unguarded context like dynamic cheat sheet scores a 70.7, which, looks great at first glance. It suggests strong performance on familiar tasks.
But as we just saw, it collapses everywhere else. Meanwhile, RSEA hits a 69.3% on a single pass, beating React's 64.6%. But then, when you give RSEA retry logic, it hits a massive 79.4%. That's the best overall result across all methods, proving RSEA completely avoids the brittleness of overfitting while still capturing massive performance gains.
Which brings us to Section 5, monotonic safety guarantees. Let's talk about capping your downside risk.
By treating context evolution as a constrained search, RSEA ensures it never significantly underperforms the base agent. It's basically a foolproof safety net. Unguarded agents optimize for short-term rewards. They want to solve the immediate problem right in front of them, even if it means writing a bad rule that will break a future task. RSEA's strict validation gate shifts that whole philosophy to guarantee non-regression. If evolved context would hurt the agent on unseen data, it just falls back to vanilla React. You cap your downside risk while fully preserving your upside potential.
Finally, Section 6, Best Practices for Developers. Here's how you upgrade your pipelines today.
If you want to stop context collapse in your production deployments right now, there are 4 mandatory steps to implement. First, decouple evolution from execution. Do not update context in the same pass that generates actions. Second, pin your validation splits. Never use the same distribution for both learning and selection. Segment a fixed percentage for offline validation. Third, implement fallback gates. If the new state degrades performance, revert it. And fourth, benchmark across multiple diverse domains like planning, tool use, and web interaction so you catch overfitting early on.
I love this quote from the paper because it perfectly summarizes everything we've talked about today. Simply dumping unstructured data into your context window degrades your agent's focus, increases latency, and totally destroys reliability. More context is not inherently better. Smarter, validated, and rigorously audited context, that's what actually pushes agentic performance forward.
So I'll leave you with this final thought to challenge how you're constructing your AI pipelines. Are your self-evolving agents truly generalizing, or are they just cramming for the wrong test? Building up brittle, unvalidated cheat sheets is a recipe for disaster. I highly encourage you to review the original paper by Nguyen, and Vuong to get all the technical details on the RSEA framework. Thanks for hanging out with me on this explainer, and I'll see you in the next one.